Hello everyone. In this video, we are going to be learning about isotopes, average atomic mass, and how to calculate it. So, to start out, let's define what an isotope is. An isotope is an atom or a set of atoms rather, that have the same number of protons but different numbers of neutrons. So, first and foremost, what you want to understand is that every single element has multiple isotopes, right? And to be defined as an element, you have to have the same amount of protons. Hydrogen, for example, has one proton. No matter what isotope of hydrogen we are talking about, there is always going to be one proton. The thing that can vary in isotopes is the amount of neutrons that are present. In that way, isotopes are also going to vary in their mass numbers. So let's take a closer look at these three isotopes of hydrogen that are listed here. We can see that in all three of them, there is one proton listed in blue right there. That is what identifies those atoms as a hydrogen atom in all three cases. We can also see that in our isotope on the left-hand side, which is labeled as hydrogen 1 down here, there are no neutrons, right? So that isotope has one proton and 0 neutrons. Isotope number 2 in the middle, or hydrogen 2, also called deuterium, has one proton still because it's still hydrogen, but this time it has one neutron. Isotope number 3, also called tritium, has still one proton, meaning that it is in fact hydrogen, but this time it has 2 neutrons. All right? And so because of that variance in neutrons, we can see that there are different mass numbers. So for our isotope on the left-hand side, hydrogen 1, we can see that that has a mass number of 1 because there's only one proton. And as we learned last note's video, protons weigh approximately 1 AMU. For our isotope in the middle, hydrogen 2, we have one proton and one neutron, totaling for a mass number of 2. And for our isotope on the right-hand side, hydrogen 3, we have one proton and 2 neutrons, totaling for a mass number of 3. Okay, so that is isotopes. We have elements that can have differing amounts of neutrons within them, but they are still the same element. All right, now if we think of the periodic table, right? We think about that little square, so I'm going to draw it for you over here. Think of hydrogen. Its atomic number is 1, but its mass number, or average atomic mass down on the bottom, is 1.008 if you look on our periodic table. Now, none of these three isotopes had a mass number of 1.008, so where is that number coming from? Well, in a sample, let's say I pulled a sample of hydrogen out of the air. Some of that sample is going to be hydrogen 1, some of that sample is going to be hydrogen 2, and some of that sample is going to be hydrogen 3. So if we think of any gas sample as a little pie chart here, just switch colors real quick. Roughly 99-ish% of that entire sample is going to be hydrogen 1. However, some of that sample is going to be hydrogen 2. And then some of that sample is going to be hydrogen 3. It just so happens that hydrogen 1 is the most prevalent isotope in any given sample of hydrogen. And so if we take something called a weighted average of that entire sample and we factor in how prevalent each isotope is into that calculation, we come up with an average atomic mass of this. And it's close to 1 because hydrogen 1 is, again, the most prevalent isotope in any given sample of hydrogen. All right? So how do we calculate that? How do we calculate a weighted average? We're going to do that with this formula right over here. And that formula states that the average atomic mass is equal to the mass of each isotope times its percent abundance, right? And if we total all of those up, they're going to equal our average atomic mass. Couple of things to note about those values. Our mass of each isotope, that's going to be our mass numbers, right? And so that, in the case of hydrogen over here, our mass of isotope 1 would be 1. In the case of hydrogen over here, our mass of isotope 2 would be 2. And we would have a third one, our mass of isotope 3 would be 3. Now, our percent abundances are different. The abundance is like percent total, but it's percent total in decimal form. And so what that means to you is that if I said, hey, guess what? Hydrogen 1 is like 99% of all hydrogen, you can't write 99% in that formula. You have to write 0.99 because that's how you express 99% in decimal form. If you're confused about how to convert a decimal into a percent or vice versa, if you got a percent, all you got to do is scooch that decimal to the left 2 places, right? So even if you have a really, really tiny percent, let's say you have 0.4%, it's still in a percent form. So you're still going to take that decimal and scooch it over 2 places to the left. And then your new number would be 0.004. All right? So let's practice using that formula. Down here, we're still using hydrogen as our example. We have, if the percent abundance of hydrogen 1 is 99%. All right, we have hydrogen 1 is 99%. That's our isotope 1. We have hydrogen 2. Its percent abundance is 0.75%. So that's isotope 2. And then finally, we've got hydrogen 3 is 0.25%. I want to know what is the average atomic mass of hydrogen. So what we're going to do is we're going to take these values and we're going to calculate the weighted average of these hydrogen isotopes. And what we should get is we should get somewhere close to what is on the periodic table. So I'm going to show you how to set that up. For isotope 1, our formula states that we need the mass of isotope 1 times its percent abundance in decimal form. Remember, our mass of isotope 1 is 1. Its percent abundance is 99%, but I have to write it in decimal form, so I'm going to write it as 0.99. Okay, so that's isotope 1. And that's dealt with right there. Now, that is going to be added to isotope 2's stuff. Remember, our mass of isotope 2 is 2. Its percent abundance is 0.75, so I have to turn that into a decimal first. And that's going to be 0.0075. That's going to be added to isotope 3. Remember, isotope 3's mass is 3. So we're going to take 3, we're going to multiply it by its percent abundance in decimal form. Again, its percent abundance is 0.25%, so we're going to turn that into a decimal form. And then all we have to do is total it up. All right. Now, we got to plug all that into a calculator. When you plug all of that into a calculator, you are going to get 1.0 1, 2, 5. That's what pops out of my calculator. You're going to round that to 2 decimal places. We're going to ignore sig figs here because sig figs are, the rules for sig figs break a little bit when you're dealing with isotopic masses because isotopic masses are considered to be true values. So again, we're just going to go ahead and ignore sig figs and we're going to round that off to, I'm going to say 2 decimal places as a rule, and we're going to round that to 1.01 AMU. Now, if we recall from my cool drawing of hydrogen up here, the true average atomic mass is 1.008, which is actually pretty close to the number that we calculated. And so we can tell that we did it right. All right, next problem. This one is going to be a touch harder, okay? So this says helium has 2 known isotopes. We have helium-4, so that's going to be our first isotope. And we have helium-5. So that's going to be isotope 2. Given that, the average atomic mass of helium on the periodic table is 4.0026, so I'm going to label that average atomic mass. What are the percent abundances of each isotope? So for this one, we actually have 2 unknowns. We don't know the percent abundance for isotope 1, and we do not know the percent abundance for isotope 2. So we have 2 things to solve for. That's why this one is just a little bit harder. We are, however, going to use that same exact formula to write out what we do know. We do know the mass of our first isotope. So let's take that mass, 4, and we're going to multiply it by an unknown abundance. In this case, it's going to be X. We do know the mass of isotope 2, 5, and we're going to multiply that by another unknown abundance, Y. And we know that all of that is equal to the average atomic mass on the periodic table, 4.0026. Okay? We can't solve this problem yet, though, because we have 2 variables, and we know that we can't solve with 2 variables. But we're not done setting up this problem, because we know, since there's only 2 isotopes, both of those isotopes together have to represent 100% of that overall sample, right? So our 2%, %1 and %2, have to add up to 100%. In decimal form, if I convert both of those unknown percents into decimal form, they're going to have to add up to 1 in decimal form. So we can express that mathematically. We can say, draw a little squiggle line, that X plus Y is equal to 100%. We can also state that in decimal form, X plus Y is equal to 1. Since decimal form is what's going on in our formula, I'm going to use this equivalency real quick to rewrite Y in terms of X. And we can do that by subtracting X on both sides. And so if I rewrite this real quick, I get that Y is equal to 1 minus X. This is what I'm actually going to plug in to my formula. All right, I'm going to substitute 1 minus X in for Y. And so I'm going to do that real quick. I'm going to rewrite it. 4 times X plus 5 times 1 minus X is equal to 4.0026. Okay, so now I only have 1 variable and I can totally solve this problem, right? All I have to do is work out my algebra. So we get 4x And to do this, I'm going to distribute this 5 to both of those things inside that set of parentheses. So we get 4x plus 5 minus 5x is equal to 4.0026. We can totally combine these like terms right here. And so if I rewrite that again, I get 5 minus x is equal to 4.0026, right? We can then subtract 5 on both sides, and we get that negative x is equal to negative 0.9974. We can divide both sides by -1, and we get that x is equal to 0.9974, right? So we just figured out this guy, right? So I could write that in percent form too to figure out the percent of isotope 1. So our percent for isotope 1 is equal to 99.74%. That's one answer. Isotope 2, on the other hand, we have to figure out still. Our percent for isotope 2 is equal to 1 minus, or in this case, 100 minus 99.74%, which is going to be equal to 0.26%. And that is our second answer. So again, this problem, a little bit harder than the other one. Most of the problems you're going to see in this class are going to mimic this one. There might be a challenge problem or two that's more like the second one, but again, by and large, you're going to be solving ones much more like the problem on the left. If you're still struggling with understanding isotopes or calculating average atomic mass, please come talk to me.